So hindrance to the progress of the deadlock to the processes is called a deadlock condition. So when one process is waiting for another process to complete and get the resource from it, and they are basically mutually waiting for each other. So that condition is called deadlock. So this condition we are going to talk more about it. What are the scenarios when a deadlock can be there? How we can actually prevent the deadlock, how we can actually avoid the deadlock. So different scenarios we are going to discuss, and those scenarios would be focusing on why this deadlock would happen, because the resources are being shared. So how we can avoid that. So this deadlock situation is happening in a multi-programming environment. So we have been discussing over and over again that the operating system is managing the resources, it is managing the processes or threads efficiently, so that we can run the multiple processes or threads concurrently or parallelly. So some features are related to the hardware, where we have more cores available to run the processes. Some features are related to operating system, where it is able to schedule different processes. So and enables concurrency by using context switching. So concurrency is basically created by the operating system, which switches the processes in between to utilize the CPU better. So this is happening when we have multiple threads running at same time. So if multiple threads are running at same time, number one, they are competing for CPU to be allocated to them, and that's why we discussed about CPU scheduling. Number two, they also want to acquire the resources. Now, resources could be different, like it could be your USB drive, your disk drive, your file, or a particular location, or itself a mutex or a semaphore. So semaphore is also working as a resource for the process. So thread basically requests a resource. If the resource is not available at that time, then thread enters a waiting state. So this is very much clear to all of us, that if the resource is not available for that particular thread, it will go into the waiting state. So whenever that resource become available, thread would be coming to ready and become ready, and it would be then allocated to the CPU for execution. Sometime a waiting thread can never change the state, because the resources it has requested are held by other waiting threads, and this situation is called deadlock situation. So we define the deadlock as a situation where every process is waiting for an event to be happened. Uh, so before we actually go deeper into deadlock and its discussion on algorithms, so first we need to look at how this all structure of the system is there. So that is basically called system model. In system, there are a finite number of resources. Those are distributed and shared among the competing threads. So it may be your CPU cycle, your files, your IO devices, and moreover your mutex logs. They are also system resources, and these are the most important resources which create a deadlock, because whenever there is a shared resource, even a shared memory, we were saying that to synchronize different processes, we were using mutex log or semaphore. So if we have, even for a single access to the to a particular location, we are using mutex log. So you can imagine how many number of mutex logs would be there, and if the threads would be competing to acquire these resources to enter into the critical section. So the process when acquired the mutex log can enter into the critical section, otherwise it will keep on waiting. So we have discussed about algorithm. We know this situation is could come up whenever two processes are entering into the critical section. So what is critical section problem? It's something which is shared by more than one process or threads. So that becomes the critical section. So it was on contemporary computer system, this was the most common source of deadlock. And threads are basically request an instance of the resource. Now each resource could have multiple instances. This is very important. So each thread, let us suppose you have 4 CPUs with you. That's 4 cores basically. So the instance would for the CPU would be 4. So there are 4 instances of that particular resource. So in that case, if we allocate one instance of a resource to any process, and that would be satisfying the thread requirement, and because a thread would require to run to execute. If we allocate that thread to CPU 1 or 2 or 3 or 4, all are same for that particular thread, and that would actually satisfy the need of the thread. So what I mean to say, each type of resource would have certain type of instances, certain number of instances. So it may be 2 instances of the same resource, 3 instances of the resource, 4 instances of the same resource. So any number of instance, all would be same, of all instances would be of same capability. Any one of the instances can be allocated to the requesting thread, and it will actually serve the purpose. So we have now resources are numbered as R1, R2, Rm, and let us suppose we have finite number of resources, and each would be something. Examples are CPU cycle, memory space, IO devices, and each would have number of instances. Let us suppose R1 has 4 instances, R2 has 3 instances, and R3 has, let us suppose, 6 instances. So how many each can serve? So R1 can serve 4 threads, R2 can serve 3 threads, and R3 can serve 6 threads at the same time, because it has these many instances. So instance means a copy of that particular resource. So it has basically, if I talk about the CPU, it has 4 cores. So it can actually allocate any one of the core to any one thread, and this is what is an instance. So the number of resources requested may not, and now the another thing is the number of resources requested by any thread should not exceed the total number of resources available in the system. So I mean to say that in a system, threads are running and they are requesting resources. Now resources are finite. They are shared between many processes or threads, and they are finite. So we need to know that how many are resources, how many are their instances, and how we can actually allocate to the thread so that the deadlock condition should never happen. If you remember in the last lecture, we discussed about the philosopher problem. In that, the resources were the chopsticks. So all 5 basically threads, philosophers, they are thinking, mean executing, running, and they need to eat, mean they need to access the shared space or shared rice bowl using a resource called chopstick. So it may be possible there is a condition, typical condition, when deadlock would occur, and that typical condition is that everyone, all of them, started eating together. And so the deadlock condition is a rarest condition that may happen in your system when all processes which are accessing the same started at the same time. So this is what is a deadlock condition, and this would create waiting, a prolonged waiting for all the processes, and anyone would not make any progress. Any process would not move forward. So that is the problem, and that is called a deadlock condition. So for each process utilizing a resource, so how it is done, it will request the resource, it will use the resource, and it will release the resource. So use, request, use, and release. So this is basically the three steps that are there. So for request releasing, there are like different type of calls, system calls available, like request and release for a device, open and close for a file, allocate and free for memory system calls. So these are basically used to implement request and release for different type of resources we have available onto our computer system. So we remember wait and signal are basically operations on the semaphore. So Mutex has operation of acquire and release. So these are the functions, those are applied for the requesting the resource and for releasing the resource. So these are system calls. So using these system calls, a particular thread would be requesting for a resource, and once done, it would be releasing that resource. So the process is request, use it, and release it. So all are happening through some system calls. To illustrate the deadlock, so basically, as we have discussed, that deadlock is a state where no process in a set is making progress. So no process is making a progress. It means that all are waiting indefinitely and the system is at halt. So I remember usually what happens is Linux or other system, when they freeze, even the Zoom app sometimes freezes. In that case, what we do, we restart our system, or the best way, whenever you find a bug which you cannot actually resolve, you cannot find a solution, the best way for a computer science person is to first restart your operating system or restart your computer system. That would take away, so many problems itself. So in that case, if that situation would be happening, then we have to reset them all. And for resetting, either we have some algorithm or we restart our computer. So if it is a program, so that in this situation, the sources are represented as chopstick and all become hungry at same time. This is very rare. Like, this condition is very rare, that all become hungry at same time and all picked their left hand side chopstick at exact same time. This is very rare condition, but it happens. So that would bring the deadlock for us. Okay, now deadlock in multi-threaded application. I think we have discussed the similar code in the previous examples also, but here I'm going to share it again. I was saying is, in multi-threaded application, we create mutex lock and then we initialize them. So here, this is an algorithm that basically creates two threads. It's basically using two mutex locks. So mutex1 and mutex2. So it created it and then tries to acquire them. So after this is done, lock and unlock are used for requesting the mutex, first mutex, and then pre-thread mutex lock is used to acquire second mutex, and whereas unlock is used to release the mutex lock. So here, this program is trying to acquire first mutex and then the second, whereas this program or the thread tries to acquire the second mutex first and then the first mutex in the second position. So for that, what would happen? Now, if they are running in a sequential manner, then there is no deadlock condition. If they try to execute concurrently and at same time, the first thread, this particular thread, let us suppose this is T1, this has acquired the first mutex. And after this is done, this thread executed in parallel or in concurrent, and it executed this statement. So what does it mean? This T1 acquired mutex first, T2 acquired, the second mutex. Now, this would again, let us suppose run. This is a hypothetical situation. Like what would be basically they are running now. This would run and this would run. Then it again started running. So in this case, if this is running, then the second lock is already acquired by the thread 2. It is not releasing it. Now this, if let us suppose this goes into wait state, and then the thread T2 would start running, and the next instruction for T2 thread is that it tries to acquire the first mutex, which is already taken by thread 1. So what would happen? This T2 will keep on waiting for the first mutex. T1 would keep waiting for the second mutex, and either of them would not make any progress. And this particular situation is called a deadlock situation. Okay. Now there is another situation, and basically this is kind of a solution also for deadlock, but this also sometimes goes into a problem. Remember, we discussed about liveness in chapter 5 or 6. So in that we discussed about liveness is that all processes are making progress. If they are not making any progress, then it is called liveness failure. Deadlock is one situation which is a liveness failure. So if there is a deadlock, we call that it is a liveness failure. Then we have another situation which is called a live lock. Now, while live lock is used to prevent deadlock, but itself it goes into the problem. It is another kind of failure, liveness failure. So it is similar to deadlock, as both prevent 2 or more threads from proceeding. So both are similar. So what it creates and deadlock created, both are similar, and it stopped the progress, but it is not similar because the reason is different for each. Now in deadlock, because T1 and T2, they have acquired the instances, and they are waiting over the instances which are acquired by other process. This would be very clear when we go for diagramming and all that. So just bear till that. In livelock, what is done? pthread, it is using a function called pthread mutex try lock. So what it will do, it will try to attempt a mutex lock without blocking. Okay, so let me move here. This will be a little clear. This is little clumsy here. I don't know how it happened, but let us suppose there are 2 threads. Okay, so now thread 1, what it is doing is int done is equal to 0, while done is not, while not done, it started acquiring the first mutex. So this is the modification to the previous code. Pthread mutex lock, so it will try to acquire first mutex. Okay, then before it tries to acquire this, there is an if condition. If pthread mutex try lock, so it will try for this. If the second mutex is available, it would be acquired. If it is not available, then in that case it will keep on failing. This statement would keep on failing. This function would keep on failing. This would also happen then when we have basically we try to use this particular function where it checks first. So what try lock is doing, it checks for the availability of the second mutex. If it is not, then it will keep on checking whenever it becomes available. But this would make this try lock to fail so many times till the time it is acquired by another process. So this failure, basically the pthread mutex here. Now let us suppose thread T1 and thread T2 started executing at same time, the same situation at same time it is happening. Okay, then this would execute this particular instruction. Let us suppose they are just running in parallel. So pthread mutex lock acquired this, and here the T2 acquired second lock. Now the next instruction is this. What would happen? Because pthread mutex try lock would try on first mutex, whereas in thread 1 this would try on second mutex, and they are again just keep on failing. This is also this is called a live lock situation, where the processes or threads are not making progress without going into the deadlock situation. So this situation is very rare, but it may happen in your operating system. So when live lock is happening, this is very rarest, but the threads are not making any progress. So the outcome is same, but the reason is different. While not done, this will keep on checking. Okay, so this will, once it is acquired, it will do some part and then unlock the second, then unlock the first and complete it done. If done is basically, if this is not happening, another part, if this is not happening, now if this condition is there, keep trying is getting failure. If this is happening, now the new modification for this is that it releases the first. Okay, so if this is not true, then else condition would work, and else condition says that the mutex lock, the first acquired lock, should be released. Okay, so in this case, what would happen? T1 would release the first mutex, whatever it has acquired. So whatever it has acquired here, it will release that. The same situation would happen for T2. Now, if it has acquired the second mutex and the try lock fails, then the else condition would work. What is else condition? That it would unlock the second lock, so with whatever it has acquired. So the modification is that if the try lock fails, then it is going to release the resources it has acquired already, and then again going to try, then again going to try. So because again going to try, it may be there that both would not sync again and not started again, because it also depend upon the CPU scheduling now when they would be scheduled next. And it may be possible that this try lock failure condition would never happen. It may be possible that T1 given to CPU earlier than T2, and they run in some sequential ordering, and they do not create the problem of live lock. What would be the benefit of adding this else condition? So let me make it a little clear here. So coming back, so this is T1, this is T2. We have used try lock here. If the try lock, this T1 started running, okay, at random time, we don't know. This will acquire this will acquire the second mutex, and it will do the task. Let us suppose again the situation come that they started running at both same time. It will acquire the first, then try for the second, which is already acquired by T2. In this case, the else part would run. So what is else part? It will release whatever it has already acquired and again try, because this is while, and done is still 0. So this will try. Done is change here inside this only. So done is not 1. Okay, so it will try basically again, and in that case it may be possible that they start at a different situation. Now this whole logic is coming from network theory. Now in the network communication networks, what is done? There are computers, those are sharing a resource. Now resource is bus. So what is bus? Basically they are sending the data onto the same channel. So this is a channel, they are sharing same resource, that is called bus. Let us suppose this is C1, C2, C3 and C4, and on a random time, let us suppose t is equals to 10, both C2 and C3 started sending data. So this also starting sending data, this also started sending the data. Now, if both datas are going on a single line, like if it is a single line and two started sending the data, then it will be called a collision. So collision of the data. When collision is there, it is usually detected back by the systems. So collision is detected, like more than one computer is sending the data onto the system. So the algorithm was, whenever collision is detected, they choose a random, they wait for a random time rather than just whenever collision detected, they would again try to send it. Rather than doing that, they wait for a random time. Let us suppose it waits for 10 milliseconds. It waited for 20 milliseconds. So in that case, both would wait for some random time and then again try to send the same. So this can also be implemented here. So whenever there is the trial live lock happening, whenever trial lock fails, it may be possible that we add in some time, buffer time to wait, and then try to acquire the lock. This is one remedy for that. Okay, so what are the actual conditions for deadlock? When the deadlock would happen? Deadlock requires these four conditions to happen together. Four. So mutual exclusion, this we discussed in the previous chapter when we started discussion about synchronization. Only one process at a time can use the resource. This is one, like the resources are non-shareable. They should not, like more than one process should not try to acquire and work into that particular resource. Now there are some non-shareable resources like reading a file. That is a non-share, that is basically that is a shareable thing. Now mutual exclusion is that your resource is non-shareable, whereas reading a file is shareable event or resource. If you want to read a file, that is a shareable thing. Like multiple processes can read from the same resource at the same time. But if it is non-shareable, like we are updating and performing some write operation, then mutual exclusion should always happen. So this is what we have already decided and discussed in the previous. So mutual exclusion, when we have a non-shareable resource, this should happen. This is one thing that number one, this would actually be the characteristic. If all these four conditions are happened together, then deadlock would certainly be there. So hold and wait. If we are following a method where one process can hold at least one resource while waiting for another process. If this is also true, like we have an algorithm where we allow this. If our operating system allow these four conditions to happen together, then certainly the deadlock would happen. Hold and wait. A process holding at least one resource and is waiting for to acquire additional resources held by other processes. This is called hold and wait condition. So mutual exclusion, hold and wait. I hope this is clear. Non-preemption. A resource once is acquired by some process can not be preempted. It means that whenever a resource has already used and released the resource, only then it will be free. That particular resource, let us suppose R1 and T1 is using this resource. Let us suppose T1 is using this resource. It cannot be, this T1 cannot be preempted. If you remember in the previous chapter, we discussed about priority inversion. Why this was happening? Because whenever a resource is acquired, a mutex lock is already acquired by some process, it cannot be preempted. If it is preempted, certainly that would create a problem. So non-preemption, resource can be released only voluntarily by the process holding it after that process has completed its task. Okay, so this is also the third condition. Now the fourth condition, if you remember in the previous chapter, we discussed about bounded time. Like each process should be given a bounded time to actually get executed when we talk about synchronization. So basically what we were saying is, if the process or a thread which is running, and it should be waiting for, if this is running, and this will check for all the processes which are next to this in this array. So it should be happening like this would look for this, and this will look for this, if this will assess for this, and then this is how we actually give the time and allocate that particular variable. We make this flag as true or false. J is equals to true or false. So this was the condition basically, because we are going from an array, and this process, whenever it has done the task, it will make the flag for true for one of this particular, and move the mutex to this particular side. So that's why it was giving a bounded time. So the same thing is happening here. The circular wait is this. So once this will actually check for P0. So all are rotating in a circular way to share the mutex, and this situation is called creates a bounded time. And now this situation is going to create a problem of deadlock. So whenever there exists a set of processes waiting such that P0 is waiting for the resource that is held by P1, this is waiting for the resource held by P1, P1 is waiting for the resource held by P2, and P2 is waiting for the resource held by P3, and so on, and Pn is waiting for the resource which is held by P0. So this is basically creating a circular wait again. So the same process, due to bounded time, so the same process is happening here. Because of that, this circular motion, there would be a deadlock condition. We will come back to this particular section again. Like all four conditions must hold for a deadlock to occur, and the circular wait condition implies hold wait. And so all four conditions are not completely independent. So these are all basically somehow dependent conditions. So when all are happening together at the same time, then the deadlock would happen. Okay, now interesting part, the resource allocation graph. So whenever we talk about resources, we can use resource allocation graph to actually see and check for the condition whether a deadlock would be created or not. Okay, so whenever we talk about graphs, a graph has vertices and edges. Each would be having certain manner. Okay, thank you. So let us suppose we create a V is partitioned into two types. Now vertices are of two types for us. First, the task, which the threads, which set consists of active threads in the system, and then R type, which set consists of resources in the system. Okay, threads are represented as a circular symbol, whereas resources are represented as rectangles, and the instances for this resource are represented as dot. So this means, let us suppose this is R1. So this means that resource R1 has 3 instances of it. So this would actually help you to understand how we are doing. Okay, so we will discuss two scenarios. One, where each resource has only one instance. Second, where each resource has more than one instance. Okay, now we have threads. Those are trying to acquire the resources. There would be some resources which would be actually allocated to some threads. Okay, so these two situations are there, which we are going to discuss. Now, whenever a thread wants to acquire a resource, this would be called a request edge. So the edge here would be two type again. Now the request edge, whenever it is directed from thread to R, and then the assignment edge when it is directed from resource to the thread. So this is request, this is allocated. Okay, so now the symbols are, this is thread, this is resources, so we have 4 dots, so it means it has 4 instances. Now whenever your thread request our instance, so we represent like this. Okay, so we modify this as T, we modify this as T. Now whenever it requests a thread, a resource, so I represent by this, and whenever it is basically allocated, now you can see here one instance is allocated. Let us suppose there is another thread which is requesting and allocated. So now I can make it like this. So a symbol or the edge that is coming from instance to that particular thread is called allocation, or we can call that as an assignment edge. This has been assigned. So this has been assigned. Okay. Now let us see at the deadlock condition. Now what is happening here? So there is a T1 is requesting for the second mutex. So this is a resource. Let us suppose this is R1 and this is R2 and this is R1. So okay, this is thread T1 and thread T2. So thread 1 is requesting for the second mutex, and it has already acquired one instance of this mutex. It has already acquired. And what happens to thread T2? It has already acquired second mutex and requesting for the first mutex. So this creates a deadlock condition. This is a deadlock condition. So basically, this is easy to judge what would be a deadlock condition. Now, when a cycle is there, whenever there is a cycle, so in that case, we can judge that a deadlock can happen. Okay, so whenever there is a cycle present in this graph, that condition would create a deadlock or can create a deadlock. We would modify this situation, because if there are more than one instances, it may or may not be a deadlock condition. But if there are only one instance, then it is a cycle is surely a deadlock condition. Okay, so now let's move to this situation. Let us suppose we have 3 sets. Now 3 sets are, one is T1, where we have, it is representing the number of threads, T1, T2, T3. Then we have resource set, where we have resources R1, R2, R3, and R4. And then we have edges. So we have variety of edges, T1 to R, T2 to R3, R1 to T2, R2 to T2, R2 to T1, and R3 to T3. So if in your question, this may be given to you. In the question, this may be given to you, and then you have to identify whether it is going to create a deadlock condition or not. So you have to judge that. So how we do that? Let's create it one by one. So there are threads. This is already done here. Okay. So there are threads T1, T2, T3. Then there are resources R1, R2, R3, and R4. So there are 4 resources. Each resource would have a number of instances. So R1 has 1 instance, R2 has 2, R3 has 1, and R4 has 3 instances. I think till here it is clear. Now the states, the edges, we are going to connect the edges. Resource T1 is requesting for R1. So this thread, this particular edge, T1 is requesting for R1. T2 is requesting for R3. So this edge. Then R1 is allocated to T2. Now R1 is allocated to T2. Okay. And then R2 is allocated to T2, and R2 is allocated to T2. and R2 is allocated to T1. So because R2 has two instances, so it is possible. Then R3 is allocated to T3. So this is basically a graph. Now, what we need to do is to identify the cycles. Okay, let's move to another. Do we see any cycle existing here? So what would happen? Let us suppose cycle is basically we start from a thread. We start from a thread R1, T1, sorry. So from T1, we go to R2. Now, what is the situation? Why this deadlock would happen? See, T1 is waiting for R1 to get freed, and R1 is allocated to T2. T2 is waiting for R3 to get freed, and R3 is waiting over T3. Okay. So now this is not a cycle. So there is no cycle here. Okay. So let us suppose I add in another. So T1 is waiting for R1 to get freed. R1 is allocated to T2. T2 is waiting for R3 to get freed, and R3 is allocated to T3, and T3 is requesting for R2 to get freed, and then from R1 we reaches this particular T1 because R2 is already allocated to T2. Now this situation is, in this situation, what is the status? So T1 goes to R1, R1 goes to T2, T2 goes to R3, R3 goes to T3, and then your T3 is requesting for R2, and R2 is allocated to T1. Okay, so this creates a cycle now. Okay, because ending and starting is same, so it is basically a cycle. So when this situation is happening, we have a deadlock condition. Okay, so how this would happen? So T1 is allocated, R2 is allocated to this one, then this one, then this, and this, and we come back here. This is one cycle, cycle number one. Now there is another cycle which starts from T2, then goes to R3, then goes to T3, then goes to R2, and then goes to T2. So this is another cycle. So there are two cycles which are existing. Okay. So once there are two cycles, we say there could be a deadlock condition. We go back now here. So if I see now this is a simplest condition where there is no deadlock existing. Okay. So in this case, R2 is actually allocated to T1. T1 is requesting for R1. R1 is allocated to T2. T2 is requesting for R3, and R3 is allocated to T3. So once our T3 is over, this is done. This resource would be freed. This would be allocated to T2. Okay. Once it is done, it will go back. Now it has all the resources, because what would happen then? This would be allocated to R3. So once this is done, this would be allocated to T2. When all the resources are available to a thread, its job is done. Okay. Now once its job is done, it will execute. The resource R1 gets freed, and when it gets freed, it will be allocated to T1. And once this T1 is completed, these two resources would also get freed. Now we come to the complex situation. Now in this case, I added another extra edge, where T3 started requesting for R2. Now let's see what would happen. T1 is requesting for R1. R1 is basically held by T2. T2 is requesting for R3. R3 is held by T3, and T3 is basically requesting for R2, which is blocked by T1 and T2. Now from T2, T1, we have a cycle. This is a cycle. From T2, we have another cycle. Now R2 has two resources, and both the resources are in cycle with this T3. So in this situation, no one is going to, because this is not going to complete until R2 is allocated to T3. If this is not going to complete, R3 is not going to be freed. If R3 is not going to be freed, T2 would not be freed. If this is not freed, R1 would never be freed, and all these three are going to wait. Okay, now we do another thing. Like, I just want to create another graph. Let us suppose there is a situation. We have R1, we have R2, we have resource R3, and then we have resource R4. Okay. R4 has 3 resources. R2 has 2 resources. Now we have 3 processes, T1, T2, and T3. T1, T2, and T3. Okay. So now one instance of R2 is allocated to T1. Another instance is given to T2. R1 has only one instance, so this is requesting, and whereas R2 is allocated to T2, and this is requesting here, and this is allocated to T3. Now this is the situation. Okay, do you see the cycle, any cycle here? Can you come up with the cycle? T1, R1, T2, R3, T3, R2, and T1. Now this condition would create a deadlock. Now I create another situation. Same situation, what would happen? Let's see. You may get question like this, so please practice it if you don't know. Like, you should actually understand this. In this situation, R2 has another resource. It is allocated to T4, and there is another situation like T1 is allocated to T5. This is allocated to this, and this is allocated to this. Now I think so it's similar, but I added 2 more sources. Okay, so now there is a cycle here in coming back to the first part, this part. Okay, so in this situation, whatever we discussed in the slide, it's same. So T1 is requesting for R1. R1 is actually held by T2. T2 is requesting for R3. R3 is held by T3, and T3 is requesting for R2, which is held by both the instances. Like, one is held by T1 and other is held by T2. Now we complete this. Let us create a cycle. So first cycle is T1, R1, T2, R3, T3, and then T1. So here is basically we are following this direction. We are following these directions, and we started from T1, then T2, then R3, then T3, then back to R2, and then T1. So this is one cycle. Okay, now one cycle is there. Now other cycle is T2, R3, T3, R2, and T2. So now when this situation is there, because neither T1 nor T2 or not T3 can basically progress, because all have one resource which is required by the other resource. So this situation is creating a cycle. It has a cycle, but this is a deadlock condition. Okay, now what about this situation? First thing, so this is same, but what I did is I added 2 more threads, T4 and T5, and I added another instance to R2. Now in this situation, what would happen? Like, there are cycles, the same cycle are there. So T1, T2, T1, R1, T2, R3, T3, then R2, and then T1. So the another cycle is T2, R3, T3, R2, and T2. So this is another cycle. But deadlock would not happen here. No deadlock here. So there is cycle, the same cycle. This cycle is also available here. These two cycles are available here. But there is no deadlock condition because we have another instance in R2 which is allocated to T4, which is not part of the cycle. So when T4 gets executed, this executes, this resource R2 would be allocated to T3. So once this is allocated, this would be executed, okay? And this would be allocated to this. Now T2 has all the resources which it needs, R1, R2, and R3. This will get executed. Now back here, this would get freed, okay? Now we come back here. So once we are back, so it required two resources, it got it, and it executes. So there's no deadlock condition here in this case. Now, what is takeaway from this? One, whenever a process of each process or thread requires certain resources to get executed, because resources are shared, so it may have to wait for certain resources which are actually acquired by some other processes. Once a thread gain all the resources it required to get executed, it goes back to its running condition and it will finish itself. It will get execute, finish it up, and releases all the resources those are required by it. So once it basically releases all other resources which are waiting for that particular resource, may acquire it and run it if they got their all resources executed. So what happened here in this case? T1, because T1 was waiting on R1, R1 was waiting given to T2, T2 was waiting for R3, which was allocated to T3. Now when T3 executed, when this executed, now if we have resource here which is allocated, so once it acquires all the resources it needs to be executed, it executes and finish it. And once it finishes, it releases all the resources and this gets free and it will be allocated to the other thread. So now here the condition was T2 needed R2, R3, and R1. It got everything. It will get and finished. It will release all the resources. And once it is done, R1 would come back. It would be allocated to T1. And T1 has all the resources. Those are needed for it. And it will get executed. So everything is executed within a set. So this is how a deadlock is. Basically, we can identify the deadlock, and based on that, we can take the action. This is basically deadlock. We detected that this could lead to a deadlock condition using resource allocation graph. So now this situation is the same, like this would not happen because R2 has an extra source. So there would be cycle, but this would not create a deadlock condition as R2 get freed from this, and then accordingly we can allocate it. Okay. So basic facts are that if the graph has no cycle, no deadlock. So take away the conclusion. If a graph has no cycle, no deadlock. If a graph has cycle, and if only one instance per resource is available, like each resource has only one resource, then deadlock would happen. If it has several resources, instances per resource, then there is possibility of deadlock. There is possibility of deadlock. So if a cycle is there and each resource has one instance, certainly for surety deadlock is there. If there are more than one instances for the resources, it may be possible that deadlock can happen. We have to test it. Like the previous example we did, there were more than one instances which were available, but still it led to a deadlock condition. But for the other one, the right hand side one, which we discussed, when we had more resources in that particular instances in that particular resource, then that deadlock condition was not there. So one is necessary and sufficient condition that a deadlock would happen if there is a cycle. In case there are only one instances available per resource. Now, there are different methods of handling deadlocks. One is, don't worry about deadlock because this is very rarest condition that all philosophers would pick up, get hungry at same time. So normally operating system says, okay, I ignore the problem, and then it is up to the application developers and other implementation, those would have taken care of deadlocks. Then we have prevent that or avoid the deadlocks. So we can prevent the deadlock or avoid the deadlocks. Okay, so ensuring that system would never enter that deadlock state, because if we see, this is a state. Now this is kind of a state diagram. So this is a state of the process threads and the resources they want to acquire. So if the state is safe state, then it would not, your system would not go into the deadlock condition. So we have to identify whether a set of threads would leave this state into unsafe or not. So there are two methods that are used that ensure that system would never enter a deadlock state. Number one is deadlock prevention. Provide set of method to ensure that at least one of necessary condition cannot hold. So what we try to do is the four conditions that we discussed, at least one of them should not be true. Like all four should not be true at same time. So we try to prevent it by doing that. The deadlock avoidance, this is requiring some extra information from a thread, like how many resources it want to use while it is executing. Based on that information, extra information, we have an algorithm. We will be discussing that algorithm. That algorithm would identify whether to grant the request of the thread or not, whether allow this thread to enter into the system for execution or not. So that is called the safety algorithm. The safety algorithm would run based on the parameters which are passed by the thread, and based on that we basically allow the resources and allow the thread to proceed. So this there are two methods that that would enable the system to never enter into the deadlock condition. So prevention, again, there could be, if we want that this should not happen, the mutual exclusion should not happen. This is one thing. So this would be possible for read-only, type of situation, but they are not good whenever we have shared things. So we need mutual exclusion. If you recall, it could lead to a race condition, because of the concurrency, it may be possible that who has written to some location. So mutual exclusion would always needed, and there are some inherent logic we have implemented and we discussed. Now mutex or your semaphore, binary semaphore or your semaphore, they are non-shareable. So that's why they are basically atomic in nature. They happen, whenever they happen, they run to completion, and they are non-shareable. So mutual exclusion can never be, released or relaxed, because there are certain resources which are inherently or intrinsically non-shareable, just like mutex and semaphore. So basically what I mean to say is that we can release a mutual exclusion thing, like for preventing deadlock. We have four situations, four conditions, and we can think of relaxing at least one out of it. Okay, so first we started thinking of whether we can relax mutual exclusion or not. So mutual exclusion basically is not required for shareable resources, but must hold for non-shareable resources. So impact you have already seen, okay? And mutex lock or semaphore, they are particularly designed for synchronization so that they are non-shareable, and they are the main source of deadlocks, basically mutex, and because there are lot many who are running, and there are lot many they are shared by threads, so they are the main source of deadlocks. So this condition cannot be relaxed, basically what I mean to say in short. So hold and wait must guarantee that whenever a process requests a resource, it does not hold any other resource. It may be possible, what can be done? There are remedies for it. Now, let us suppose if this is the condition, it will enable that if a process would not get its resource, it will release the existing resources which it is holding. Now we discussed in try lock, that if the second mutex it cannot obtain, it will release the first one also. So when that time would come when all the resources needed by the thread would be available, because they are shareable, so that process may have to wait for so long. And if the process has to wait so long, it would decrease the throughput of your system, for your operating system. Okay, so the problems for if we create, everything is interrelated. So if we relax this hold and wait condition, then your system performance would go down. Low resource utilization and starvation is possible if we release, relax, hold and wait condition. We also don't want to do this. Now, non-preemption. Non-preemption means whenever a resource is held by some process, we should be we should be allowed to preempt it. Like we should be able to preempt that particular thread and get acquire of resource. Now that resource is handling a mutex lock. Let us suppose a condition when a mutex lock which is required by an interrupt. Let us suppose there is a spell lock that is required by the interrupt itself, and it interrupted a process which has acquired that spell lock S1. So let us suppose there is a thread running T1 which acquired a spell lock S1. Now there is an interrupt which required the spell lock S1. Now whenever an interrupt would come, it would actually, interrupt this process T1. Now T1 has already acquired spell lock S1. In that case, again, preemption would not help us. If this is done, this would not help. So what could be the remedy? That the interrupts could be disabled for that time. So non-preemption, no preemption. If the process that is holding some resource requests another process that cannot be immediately allocated, then all the resources currently being held is released. This is number one solution to it. The preempted resources are added to the list of resources for which the process is waiting. And process must be restarted only when it regains the old resource as well as the new resources that it is requesting. So the solution number one is that if somebody requests the resource which this particular thread is holding, the non-preemption would allow this to release this resource and then keep on waiting for when it would again become free along with all other resources that it is waiting for. So basically what this says, that whatever it has acquired, release it and keep on waiting for this, including the others. So that would increase again the wait time for that particular process or the thread, also increase your lower down your throughput of the system. Alternatively, what can be done? We first check whether this is available. If available, then allocate. If not available and it is allocated to some other thread, let us suppose T1 is requesting for R1. R1 is allocated to T2 and T2 is requesting for R3. If this situation is there, Basically, T2 is blocked because of R3. So in that case, what would happen? We preempt this and release. Once it is preempted, it would release this and it is acquired back by the T1. So this is one solution of handling it. But this would again, the T2 would again starve and it will wait for long. So these are the inherent problems. If we want to relax it because of the deadlock condition, then it would impact your system performance. Now another is the circular wait. The circular wait, we discussed that the processes or threads are basically moving like this. They are circular. So T0 waits for T1, T1 waits for T2, T2 waits for T3, T3 waits for T4, and T4 waits for T5, and then T5 waits for T0. So this is how the circular wait is. Now for breaking this, circular wait actually help us to do this, other than the previous three. What is done? It is said that even if the process threads are numbered, the resources are also given numbers. So R1, R2, R3, R4, R5. So all these are numbered. So this is number 1, number 2, number 3, number 4, number 5. So based on these numbers, we can actually break this circular wait. How? Let's see. So formally, we define a function which assign each resource a number. N is a set of natural numbers. Okay. So a thread can initially request an instance of a resource, say Ri. This is Ri. After that, a thread can request an instance of Rj, the next thread and next resource, if the number Rj is greater than Ri. So if I mean to say, let us suppose this is R1, then it could request only R4. So it cannot go back to R0 or so. It cannot request it. So this is enforced onto the threads. Like this would be created, this would be dependent upon the application. They would number each and every resource, and they would allow the thread to follow this rule. So this rule says that a thread T1 can request for the next resource which is higher in number than the previous one. Okay.